the chemact4 and the corresponding sets of videos, we will explore how the technique of mass spectrometry can be used to determine the average atomic mass of an element. We begin with a cartoon where three scientists appear to be having lunch. One is lamenting that someone has processed his lunch in a mass spectrometer, and the other two scientists are looking somewhat sheepish. Of course, only those who know something about mass spectrometers would find some humor in this cartoon. By the end of this video, you will come to know that the resulting spectra from mass spectrometry looks something like the spiked peaks we see in the character's lunchbox. In case you're wondering, it is not possible to process an entire sandwich through a mass spectrometer and have a three-dimensional matrix spit out on the other end. The intended learning outcomes for this activity and video are that you will be able to describe how the mass spectrometer may be used to determine the relative isotopic mass using carbon-12 isotope as a standard, and how this information can be used to calculate the average atomic mass. Also, to calculate for one variable given the other two for the following parameters: average atomic mass, isotopic mass, and abundance of constituent isotopes. Mass spectrometry is an analytical technique that is especially important in organic chemistry, as it allows for the determination of molecular mass and molecular structure, the identification of unknown compounds, and even quantification of the amount of compound in a sample. In this activity, we're only going to focus on how it can be used to determine the mass and the abundance of each of the isotopes for an element. This slide shows a diagram that outlines the basic functioning of a mass spectrometer. The applied sample must first be vaporized. That is, all the constituent atoms must be in the gaseous phase. This is true even for those elements that normally we think of as being solids or metallic at room temperature, such as lead or titanium. The sample is then bombarded by an electron gun that projects a stream of high-energy electrons. The goal is to knock out a single electron from each of the atoms, thereby ionizing them to a unit charge. The power of the electron gun is set so that the majority of the ions that are produced will have a +1 charge. These cations are then accelerated down a tunnel. A vacuum is applied to the tunnel so as to minimize interferences from other gaseous molecules, such as molecular nitrogen and molecular oxygen found in air. Note that the tunnel is curved, so that if nothing else happened, the cations would simply strike the curved wall of the tunnel. But what does happen, however, is a variable magnetic field is applied, which can deflect the cations towards the detector. So how does all this lead to a mass measurement? As it turns out, the strength of the magnetic field required to deflect a cation is correlated with the mass of the cation. The bigger the ion, the greater the magnetic field required. The mass of an isotope is not reported, however, in teslas, which is the unit for magnetic field strength, but rather in atomic mass units. So how is this conversion done then? Well, the strength of the magnetic field required to deflect a cation can be related to atomic mass units by using a standard and calibrating the instrument. As you might have guessed, the standard used is carbon-12 isotope, whose mass is defined as exactly 12 atomic mass units. The following simulation may help you visualize better how a mass spectrometer can lead to the determination of the average atomic mass of an element. We will start with a 50-50 mixture of carbon-12 and carbon-13 set at 10 atoms each, which of course is not the natural distribution of isotopic abundance. The atoms have already been vaporized. When the atoms are released and deflected, two peaks are observed of equal height at a mass of 12 and close to 13 atomic mass units. Because in this scenario the isotopes are equally abundant, the weighted average would be about 12.5 atomic mass units. We now choose the natural isotopic mixture for carbon, which is approximately 99% carbon-12 and 1% carbon-13. Observe in the vaporization chamber that there are very few red atoms, which represent the carbon-13 isotope. The analysis again shows two peaks, but clearly there's a huge excess of carbon-12 versus carbon-13. As expected, a weighted average would give a mass closer to the more abundant isotope, of course carbon-12. While this simulation is helpful in imagining the workings of a mass spectrometer, the presentation of the mass spectrum itself is not quite typical. Let's turn to teaching model 1 to see a more representative mass spectrum for an element. We are using the element boron as an example. It might be useful to pause the video to reflect on how this spectrum looks different than the one shown in the simulation. One significant difference in the typical mass spectrum shown here is that the peaks are quite narrow, and associated with each peak is a precise readout through a computer analysis of the isotopic atomic mass to several significant figures in atomic mass units, as shown in this table. Note also that the x-axis of the spectrum is actually labeled as m/z and not atomic mass. This is typical of most mass spectrums. The m/z signifies mass per charge. You may recall, however, that the instrument is set to produce cations with typically only a +1 charge. Mass divided by +1, of course, simply equals the mass. Therefore, the x-axis, practically speaking, is the atomic mass in atomic mass units. Lastly, note that the peak corresponding to the most abundant isotope, boron-11, actually measures at 100%. This is because the y-axis in a typical mass spectrum shows relative percent abundance rather than actual percent abundance, where the most abundant peak is set at 100%. An extra calculation is required to obtain the percent abundance. An example is shown for boron-11. The idea is that we want to calculate what is the percent fraction of the 100 compared to the total abundance. As the relative abundance of boron-10 is about 25%, the calculation would proceed as 100 divided by 125, or 100 plus 25, times 100%. This, of course, roughly equals 80%. If more precise numbers had been used for boron-10 abundance, we would arrive at the 80.22% as shown in the table. You may be happy to know that this last calculation is typically done for you, and data is presented such as seen below the spectrum in teaching model number 1.